Thank you for taking time to attend this presentation. This presentation is on benchmarking graphical models on power with healthcare applications. I'm Radha Nagarajan, Director, Center for Oral and Systemic Health, Marshfield Clinical Research Institute, Marshfield Clinic Health System, Wisconsin, and I'll be tag teaming with Arghya Kusum, Assistant Professor of Computer Science, University of Wisconsin-Platteville. So a brief overview of the presentation. We'll talk about graphical models as to what these are and why they are pertinent and implementation aspects. And we'll discuss some of our preliminary results. This is work under progress. And we'll also discuss healthcare applications. So before we jump start into graphical models, what are graphs? These are essentially composed of nodes and edges. Nodes represent the entities of interest, and edges represent potential associations, including relationship between the nodes. So graphical models are essentially models that derive these associations between the entities of interest from their digital signatures. An example of a graph is shown on the lower right, where we have the nodes. This could be subjects, and edges, potential association between the subjects. So on the left, we've shown a comparative figure that essentially represents a reductionist abstraction, but each of the entities are considered in isolation. So this is more or less a univariate representation where we discuss each of these entities in isolation, and some of their properties might not readily become apparent, which warrants understanding the relationship between them. So why graphical models? As discussed on the previous slide, they can definitely reveal system-level properties and behavior, not readily apparent from the reductionist representation. So to speak, in a way, the principle of superposition fails for many of the complex systems in the real world. And system-level abstractions, understanding them are especially critical in developing targeted interventions. Examples include modeling COVID spread in a given community using approaches such as contact tracing, and subsequently using these models to assess community-based intervention policies and optimal resource allocation. So another example would be modeling the signaling mechanism in response to a pathogen and identifying the cascade of process that takes place so as to assist in drug targeting. Also, these models can have the capacity to serve as in silico models that can be controlled and experimented in a cost-effective manner. So this includes posing questions to these models that fall under inference. So given the evidence of partial information, can we make a statement on the probability of outcomes? So these associations can reveal also causal associations under certain implicit assumptions. But it is important to know that we are not attempting to decipher the true causality, but derive the causality from the observed data. So there are definitely limitations, and I wanted to explicitly acknowledge that. So what is the problem? What we have is data across a given set of entities, multivariate data, and what we need is a graphical structure representing potential association and representation of relationship between these variables. So one can ask, why can't we directly determine the pairwise dependencies using symmetric measures, such as correlation or mutual information? And that is definitely helpful, but it is important to note that association between a pair of entities need not necessarily be direct and may be mediated through a third variable or a set of variables. So this emphasizes the need to incorporate conditional dependencies. And simple example is shown at the bottom, where we have laws of taste and disease severity. As such, these are marginally independent events, but they may be related when we condition them on the fact that the subject is COVID positive. Again, there are several approaches that have been proposed in literature to decipher these graphical abstractions. One of the popular approaches based in structural learning that models the joint probability distribution across a given set of entities or informed set of variables as a product of marginal conditional probability distributions. So incorporating conditional dependencies is at the core of these approaches, and the resulting network is easy to visualize and is in the form of a directed acyclic graph. The probabilistic nature of these approaches explicitly is useful in modeling potential uncertainties in real-world data, which is ubiquitous. So an example of a directed acyclic graph is shown where we have L and D who do not have parents and affect the value of C. So the joint probability distribution of this graph is given by probability of L, product probability of D, and probability of C, conditioned on L and D. So in general, you have the equation shown below, P of X equals product of P of Xi by conditioned on pi Xi, where pi Xi essentially represents the patterns of Xi. It's important to note that there's a one-to-one map between the conditional probability distributions given as a product above and the corresponding graphical structure. So multivariate data, what is it? How does it look like? There are two forms of data that one can encounter in real world. First is longitudinal data, which is essentially a continuous process that is sampled as a function of time. These often are in the form of time series, multivariate time series, but there are certain properties that we want to preserve when we acquire these time series, so as its properties do not change as a function of time, so they're challenging to obtain. Another data that is much more common is cross-sectional data. So as opposed to time series where we have explicit temporal information, in the case of cross-sectional data, what we have is a snapshot of the temporal process. Think of it as taking a camera and taking multiple snapshots of the process in a given time window. That's what you get in the case of cross-sectional data with replicate measurements. So many of the properties and other aspects can vary. In this presentation, we don't address all these complexities. We assume that all is well and good. So here's an example of a data, the cross-sectional data that we talked about. It's shown on the left, and it's a form of a matrix where the rows represent the independent realizations and the columns represent essentially the variables of inference. So we have the data. Now the question is, how do we determine the associations and relationships between the entities? Three popular approaches for structured learning is constraint-based approach, search and score, and hybrid that uses a combination of the above two. Constraint-based approaches essentially learn the structure using conditional independence tests. Search and score learn the structure that best fits the data using research in conjunction with the chosen scoring criteria. Just to get an idea about the computational complexity of these structured learning algorithms, exhaustive enumeration as the number of nodes increases, the number of DAGs, directed acyclic graphs, increase super exponentially. This more or less challenges using these approaches, using exhaustive enumeration from practical standpoints. So another aspect that needs to be emphasized is the Markov equivalence. Although these structures look markedly different based on the direction of the arrows, it's important to note that they're probabilistically equivalent structures. So one can obtain one structure from another by directly applying the Bayes theorem. So what I'm trying to get across in this slide is that although it's even if you're able to have exhaustive enumeration, the structures that can be derived from observational healthcare data can only be up to the Markov equivalence class. So here's a brief description of the hill climbing algorithm. So how it starts is you have a random seed or your initial guess of the graphical structure. Then you choose a scoring criteria and score the structure. Then you make modifications to this graph. Then you recompute the scores. If the recomputed scores of the modified structure is appreciably greater than what we had before, then we replace the structure and iterate. And we stop this and exit the loop when we have a structure whose scores do not change appreciably from that of the previous iteration. There are some theoretical considerations for research, and the recent article discusses this. In the interest of time, we won't go into any details of this. So hill climbing approach by its very nature is a sequential algorithm. So the score of the present structure G star is generated by modifying the previous structure. However, there are opportunities for distributing the computation in the hill climbing approach. For instance, the potential structure is a snapshot of step 4, which is shown there. For convenience, the potential structure is interrogated and it can be distributed. And the BIC score, for instance, one of the scores widely used in basic structural learning, its expression, functional form, it represents some of the scores of its local structure and can be distributed. Since this is a greedy algorithm, convergence to local optimum cannot be avoided. So it might have to be repeated multiple times with different random initial seeds. Then in that case, that aspect can be distributed. And in the case the data doesn't fit into a commodity RAM, then the data, in addition to the computation that we discussed, can be distributed. So I'm gonna hand this to Argo now.
Sure. Thanks, Radha, for the nice introduction about the Bayesian network and all. So from here, I'm going to discuss about our experience on Power 9. By the way, I am Arghya Kusum Das, and I am an assistant professor at University of Wisconsin-Platteville. My research interest is mostly like big data analytics and their infrastructure and some performance related things. So here in this presentation, I'm going to talk more about our experience on Power 9, and I will do a little bit of comparison between our Power 9 experience and x86 experiences. So the Power 9 server that we have used, that is actually situated in University of Wisconsin-Platteville, that is IC922 server, which has a CPU type like DD 2.3 Power 9 and processor module. And then it has 160 virtual cores with all the SMTs enabled, and it has like access to 32 DIMMs and sustained bandwidth of 28.8 GB. We also tested, compared the performance of this IC922 server with respect to HPE ProLiant DL580 server, which is based on Intel Xeon X series processor, and it has like a number of cores per node, 16. So this actually makes a huge difference. So where Intel has only the hyperthreading, like 2 hyperthreading, and most of the times they have some kind of performance glitches, like if the data size is huge, then hyperthreading does not optimize the performance and all these things. They are actually our experience is power performed really great. By the way, both the machines have like 512 gigabytes of RAM. Next slide, please, Radha. So regarding the implementation, as Radha told, that hill climbing method, what we have done is, first of all, we have used like a HIPMAS dataset, which is publicly available, and it has almost like 10.5 million samples, and it comprises of 28 variables, all the continuous normalized variables, but we have discretized it into binary categorical variable by thresholding about their mean. And then on these 10.5 million records, we did all our Bayesian network structure learning implementation. For that, initially we have used PGMPy libraries, which has some dependencies on pandas and NetworkX. And here actually we have just the hill climbing method actually. So we have recognized, we have just analyzed the performance of the hill climbing algorithm offered by PGMPy. We have modified it a little bit and then tested the performance. So, so Radha, can you go to the next slide, please? So here is the performance. So we not only did the performance analysis for only the single threaded, rather what we were more interested to check the parallel performance, because there is where our novelty based on, and there is actually Power 9 also surpasses Intel cluster, because So what we have done is we have distributed the 10.5 million data set using the Dask APIs over the nodes of many memories. And then we have written a Hadoop wrapper on top of the PGMPy's hill climbing instance. So this is how we have parallelized our entire algorithm and then run on top of our IC922, which offers like 160 virtual cores. So the next slide, Radha. So here is the performance result, which is really great. And as you can see there, we got like significant difference in performance in terms of like Power 9 and x86. So the most of the time, we have received, when it is just a single thread, then also we have received almost like 105 times performance difference. And as you can see, these are like statistically significant difference, and you can see the p-value in the bottom of these slides. And as expected, like as I mentioned, it is like BIC scoring technique takes like very less computational time. And also we have done not only the BIC scoring, we also check the performance for K2 scoring. And as expected, like BIC score takes less computational time over Power 9 and x86 both. But if you compare the performance of Power 9 and x86, you will see a constant like 1.5 times difference. And Power 9 is of course better in this case. So can we go to the next slide, please, Radha? Thanks. So this is the performance for our parallelized workload, where we have used a Hadoop wrapper, and we have just done like, so we collected the computational time across the 5 runs of HEPMAS data with hill climbing, and we did a 2 sample t-test with unequal variance, as you can see in the slide. And and as you can see, for the first 2 places, I mean, there are like significantly different difference between the performance of Power and x86. And the best part that I would like to focus on, that after 32 map tasks in Hadoop, Intel actually started, x86 processor actually started like stabilizing the performance. We did not get more from that. But since Power 9 has this SMT, simultaneous multi-threading, so we got like a constant linear improvement in power, in performance. So this is our experience. So I think that is it from my side. And Radha, if you have anything to add on performance, you can do that, and the next part is yours.
Thank you, Arghya. So healthcare, so how does this all fit within the broad scope of healthcare applications? How does this go? Where's the nexus? So digital healthcare data has definitely seen an explosion of late. The number of source systems to generate healthcare data and obtain healthcare data has grown over time. Initially, it started off with HITECH Act and mandatory compliance and implementation in the United States of electronic health records. Then we had claims data, and then registries. The number of registries have gone, and more recently, Internet of Things have come up to be one of the dominant players from where data is being retrieved in a constant basis. So what data types that we encounter in healthcare settings also come from in different flavors. For instance, the data could be clinician notes, free text, or structured text after a certain amount of standardization. So you have the data in the form of text or images. It could be radiographic images, such as X-rays, fMRIs, or it could be physiological signals, such as EEG, ECG, or any such. So you have a compendium of data sets that you encounter. In addition to that, there's a strong emphasis on multi-scale profiling, where we want to see interrogate a given subject from different angles. So it could be molecular data, it could be behavioral data, and so we have multiple types of data sets. In fact, that flies under the broad umbrella and falls within the objective of precision medicine. And there's high throughput data in healthcare, such as those that obtain from high throughput molecular assays such as next generation sequencing. And there is also significant progress in standardizing these data sets. Several initiatives are there in place, and these have resulted in not only massive data sets in a healthcare system or organization, but pooling data sets from multiple healthcare systems or organizations through health information exchange and other efforts. And more recently, fast healthcare interoperability resources give a fine nexus to IoTs and other devices, and in exchange of data sets. So all these things culminate and contribute to the massive data explosion in healthcare. And there's also a strong trend in increasing analytics adoption. Initially, there was always concern about the storage and Hadoop and other kind of big data ecosystem came to the rescue. And but however, over time, the storage problem has more or less been handled in some sense, but there's a strong emphasis on trying to retrieve knowledge out of these data sets. These fly under descriptive, predictive, and prescriptive analytics. So the challenge increases from descriptive to prescriptive. Descriptive is more or less trying to get summary statistics, like querying the data to aggregate counts, and predictive would be predicting longitudinal outcomes. So 5 months down the line, what would be the clinical outcome, or what would be the operational or financial outcome? And prescriptive analytics is how do we come up with interventions? So, and then there's a strong shift from consensus-based or agreed upon approaches to more evidence-based and data-driven approaches that can impact outcomes as well as key performance indicators in healthcare. And then definitely, and many of you would have noted this, a surge in the adoption of machine learning and artificial intelligence approaches that includes mining natural language, such as NLP approaches, as well as imaging data. So there's a whole lot of exciting initiatives that are underway. So graphical models, we started this conversation with graphical models. How does this all tie together? So the healthcare applications of graphical models include diagnostic reasoning, prognostic reasoning. It can also assist in treatment selection as well as discovering functional associations. So healthcare data sets, for various reasons, we have not delved into this in detail, but are noisy by their very nature and multivariate. Several factors attribute to it, making probabilistic graphical models a natural choice to mine them. And many of the association between these entities are unknown. So graphical models not only have the ability to validate what is known in terms of association, but also discover new associations so as to assist in hypothesis generation as opposed to classical hypothesis testing. And deciphering this association, as discussed in the earlier slides, is an important preliminary step that can assist in targeted intervention. And graphical models fall under machine learning as well as artificial intelligence. And one of the popular classification approach, which is kind of, in some sense, a very constrained graphical model, is your naive Bayes classifier. But then in the more advanced cases where it kind of builds the nexus to AI is you can post queries to these models and kind of estimate probabilities on outcomes based on partial knowledge or partial evidence. And the nexus to causality also brings it as an approach that can complement RCTs or randomized control trials. Randomized control trials are thought of as a gold standards in treatment recommendations, but then again, they are idealized in that there's a lot of inclusion-exclusion criteria. So they really don't incorporate the population-specific digital signatures, in which case graphical models can come in handy. And definitely, they're easy to visualize and easy to interpret as opposed to some of the black box algorithms that are out there. And what we need is architectures and programming environment that can dive into these large gamut of data sets so as to derive these knowledge from it and assist in decision making. And this could also be real-time clinical decision making. So in summary, what we have talked about in this presentation and we have covered is we talked about graphical models, what they are, and how the computational aspects and how they are computationally intense. And then we shared some of our preliminary findings. There's still a long way to go. And we also built Nexus to healthcare applications. And we'd like to acknowledge some of our so the people who are played a critical role in this research and contributed from various standpoints. They are listed below, and the contact information of we can be contacted at the email below, and we'd be happy to take any questions.